Hello, everyone. Thanks for dropping in. We're gonna give it a few more minutes just to have a few more people kind of fill in, and then in a couple minutes we'll get started officially. So just hang tight. We've got a few more people funneling in here, so we'll give it another minute or two, and then we'll get started. All right, we're 2 minutes past start time here. We'll get started. People can kind of funnel in as they keep jumping in. So first of all, for those of you who don't know who I am, my name is Matt Jameson. I am the territory manager for the Waterloo office of Odell HVAC. And I want to thank all of you for coming to this presentation. It's really good info, really kind of helps get the kind of new data out there for everybody. And doing the presentation today is Anurag. He is the Director of Sales and Application Engineering with enVerid Systems. Anurag is a passionate engineer and writer with the focus on sustainable building design and operations. He's been heavily involved with ASHRAE, in particular with ASHRAE 62.1 in the indoor air quality procedure. So without really further ado, I will let Anurag take it over and run with the presentation from here.
Excellent. Thank you, Matt. Good morning to everyone. Thank you for making time to attend today's PDH session on how the Indoor Air Quality Procedure, IAQP, that's one of the many acronyms you'll hear me say today, is enabling net zero and decarbonization goals while maintaining healthy spaces. Let's get started. Quick overview of today's agenda. To kick things off, I have a few questions for you, and then I'll go into kind of what we do today, our common approach for addressing indoor air quality today. What is the alternative approach and how does IAQP fit into that? What are the benefits of that alternative approach and how updates to ASHRAE standards are creating new, easier opportunities to apply the procedure. And then with whatever time we have left, we'll go through some sample calculations, case studies, and we'll be sure to leave time at the end for questions as well. If you have questions along the presentation, please add them to the Q&A, and we'll visit those questions towards the last 10 minutes or so. So to kick things off, I have a few questions for you. Feel free to kind of answer this in your mind. Normally, I like doing this, in person, but today we'll just kind of go through these questions more casually. So the first question is, which building systems use the most energy? The answer to that is D, HVAC. HVAC energy end use can represent up to 40% of the total building energy use. And of that HVAC component, ventilation can represent up to 40% of the ventilation of the total HVAC energy use. So given how energy intensive ventilation can be for buildings, why do we ventilate buildings? That's the second question. All right, the answer to that is we ventilate buildings to maintain acceptable indoor air quality. And acceptable indoor air quality has a two-part definition coming directly from ASHRAE Standard 62.1. And that involves ventilating buildings or that involves acceptable indoor air quality as a building where contaminants are below healthy levels, and a building where occupants in the space are not dissatisfied. Oftentimes, odors is a proxy for occupant satisfaction with air quality in the space. And digging a little bit deeper, what type of indoor air pollutant should we be worried about? So you got a few options here, and the correct answer is all of them. So in a typical commercial building space, like the office building you may be sitting in this morning, we have a heterogeneous kind of mixture of different types of contaminants. Particles and pathogens largely come from OA intakes, and they're addressed through particle filters, such as MERV 13 filter. Then we have a variety of gases that come in that are also in the building. And some examples of those gases are ozone, formaldehyde, and other VOCs. And these gases are typically managed through dilution, aka ventilation. So the challenge with using dilution as our solution to indoor air pollution will be covered in the next few slides. So as many of you may know, typically in a commercial building space, we're following prescriptive ventilation rate requirements, and in return, we're replacing the full volume of air for an office building 1 to 2 times per hour, and for an educational space, it can be 3 to 5 times per hour. So we're using dilution here to help control indoor air quality. In return, when we use dilution as a strategy for controlling indoor air quality, we're using a lot of energy, right? So that energy usage is represented in this blue bar in the middle. Typically, this is in units of energy use index, which is energy per square foot per year. When you design a building using prescriptive ventilation rates, your EUI can be, in this example, this is a 100,000 square foot office building in climate zone 5A. It can be about 10 to 15%, 10 to 20% of your total building EUI. And conventionally, as a designer, you may consider increasing ventilation to achieve enhanced indoor air quality. And as you increase ventilation, you add energy. And that's represented in this yellow/orange bar on the right side. What we'll learn more about today is a new paradigm, or a paradigm shift rather, where we offset ventilation requirements with air cleaning. And to do so, we apply the indoor air quality procedure, IAQP. And in return, we can start lowering the EUI, lowering the total load on the building, and enabling us to better design for net zero buildings. More on that later. And on the right side, you see the same chart, but in units of dollars. So typically, it's a rule of thumb I'll throw out there, and is about $1.50 per CFM of outdoor air that we supply to the building. So in this example, the blue bar, the VRP bar, represents about 20,000 CFM of outdoor air. The other challenge with using dilution as our solution to indoor air pollution is that outdoor air is not always so fresh. In this graphic, you see kind of an example of outdoor contaminants coming from a variety of sources. Those could be carbon monoxide and other organic contaminants coming from combustion processes happening from cars, jet fuel from airplanes, additional contaminants from adjacent industrial properties around the project site. So really the challenge for designers, owners, and operators of the built environment is how do we enhance indoor air quality while being resilient to what's happening outdoors. And what I didn't mention in the previous slide is that we also are experiencing in many parts of North America, almost a seemingly annual wildfire season. So there's also times of the year where outdoor air quality is poor due to generation of particulate matter from wildfires. So there's a resiliency component to using perhaps less outdoor air to control indoor air quality. So the solution we'll be covering today is the indoor air quality procedure. And I'm calling it Clean First. So what is the Clean First framework? That's highlighted here in this slide. It involves 4 steps. The first step is to set targets for indoor air quality. So these targets are typically set by ASHRAE Standard 62.1. And then there's also targets available that are perhaps in some cases a bit more stringent, and those can come from project-specific lead and well requirements. There's also studies from institutions like Harvard that also help us define kind of a baseline for indoor air quality or targets for indoor air quality. The second step is to install air cleaning into the ventilation design. And this can consist of a few different types of air cleaning technologies, some treating indoor air, perhaps some treating outdoor air. And that can enable us to then use step 3, which involves using the indoor air quality procedure to right size and often downsize ventilation systems because we are taking credit for air cleaning in step 2. And then the last step, kind of an optional step, is to have a robust IAQ monitoring program in place so that we have continuous feedback on real-time indoor air quality. And through the life of the building, we can make informed decisions around indoor air quality, HVAC upgrades. So these 4 steps together contribute to what we're seeing here on the right side, which is sustainable indoor air quality. Better indoor air quality because we're introducing less outdoor-borne contaminants into the indoor environment, and achieving indoor air quality more energy efficiently. And we're also offering resiliency for the building because we're essentially offering buildings a self-contained way using localized or indoor air cleaning, using the IAQP to be less reliant on what's outside of the building. So as part of this Clean First framework, in step 3, I've referred to the indoor air quality procedure. What is the indoor air quality procedure? You may have heard of this procedure. You may have even applied this on a project or have tried to apply it on a project. But hopefully after today's session, you'll better understand the benefits of this procedure and how easy it is to apply. But simply put, the indoor air quality procedure is one of 2 procedures in the IMC, in the National Building Code of Canada, and in ASHRAE Standard 62.1 to size ventilation systems. And it sits alongside the prescriptive procedure, the VRP. And the IAQP introduces a variable for air cleaning efficiency in the calculation. I'll go through the calculation later, but the main difference between the IAQP and the VRP is that the IAQP allows you to take credit for air cleaning efficiency to then size your ventilation system. And oftentimes that results in smaller ventilation systems and reduced energy consumption. So kind of a side-by-side graphical comparison. On the left here, you see the VRP requires using brute force, I like to say, or outdoor air to control indoor air quality. The more force we put in, the more outdoor air we bring in. Theoretically, the better indoor air quality you have. Alternatively, the IAQP allows you to be more conservative with how much outdoor air you bring in because you're leveraging indoor air cleaning into the ventilation system. So that concept is illustrated here, is that we can find combinations of outdoor air and air cleaning to right size and often downsize our ventilation systems. So I also call the IAQP hybrid ventilation, and you may hear me refer to this as hybrid ventilation later on. All right, and the indoor air quality procedure lives in 62.1, but it also is referenced in the National Building Code of Canada, the NBCC, as well as the International Mechanical Code. So over here, you see that under section 403.2, you have 2 options as a designer to size ventilation systems, the IAQP being one of them. So sometimes, when I present to consulting engineers, contractors, building owners, the question comes up, is the IAQP a code variant? No, it is not. It is simply an available pathway already in codes, and the IAQP has been applied in many projects already in the province of Ontario. The IAQP is also being adopted through accelerating trends in the marketplace around occupant wellness, mandates around energy efficiency, and then of course concerns about outdoor air quality. So there's these market pushes driving IAQP adoption, and this is why I think this is a timely presentation to learn more about how IAQP can be used to address those trends. And kind of shown here in a Venn diagram is, as a designer, as a building operator, as a building, as a contractor, perhaps you have different market drivers, many around financial uncertainty, rising interest rates, rising utility rates, overall increases in cost of construction. We have market drivers around, how do we deliver good indoor air quality while being resilient to outdoor air contaminants? And then thirdly, and a big topic for today is really around decarbonization and net zero. How do we lower the building load so that we can use less renewables to offset the total building load? So all of these different market drivers, I think, are addressed through the IAQP, and we'll learn more about that through this session. Also, the IAQP and the concept of using air cleaning is discussed by a lot of industry professionals as a good approach to addressing indoor air quality. One of the quotes I really like is the one on the top left by Professor Bill Banfield, past ASHRAE president, which states that the future of really good indoor air quality is going to be alternatives to ventilation, so we don't have to rely on outdoor air for everything. So alternative ventilations, that's the clean first approach, right? Using air cleaning as opposed to air dilution. So why would you apply this? What are some benefits of using the IAQP? I can provide a lot of my own opinions, but ASHRAE, and I want to start with what ASHRAE has listed as why you would apply the IAQP. These reasons are outlined in the ASHRAE 62.1 User's Manual. And the first reason I think applies to any project you may be designing or any building that's currently operating is that the IAQP may allow for a more cost-effective solution to providing good indoor air quality, as all design strategies may be considered. All design strategies meaning not just ventilation with energy recovery, but also air cleaning and perhaps a little bit less ventilation. So again, that hybrid kind of approach to addressing indoor air quality. So some rules of thumb on the benefits that IAQP can provide is typically on a 20,000 square foot basis. We're reducing about with the IAQP, you can reduce about 60 to 70% outdoor air relative to the VRP. That equates to about 2,000 CFM in outdoor air reduction, which equates to about 10 to 15 tons in peak cooling load reduction and 100 to 200 MBH in peak heating load reduction. And this reduction in outdoor air requirements can have a systemic impact on how you size and design the rest of the MEP systems. Most notably, you can downsize your energy recovery unit, and you can free up some mechanical footprint there, reduce CapEx for other HVAC equipment. So lots of benefits there. Operationally, over the life of the building, typically on a per 20,000 square foot basis, you're saving at least $3,000 to $4,000 on a per 20,000 square foot basis. Obviously, this depends on the project location, the outdoor air conditions for that location, as well as the local utility rates, runtime hours, etc. But this is just kind of a nice rule of thumb, about 30 to 40 cents per square foot of savings available. So some of those rules of thumb are built into this graphic here. This is from energy modeling I've done showing that, let's look at maybe climate zone 5A and 6A, which I think are most applicable to the eastern part of Canada, is that if you look at climate zone 6A, for a VRP design where we don't have air cleaning, it's about 54 cents per square foot to ventilate the space or the building. And then with the IAQP, we can get down to about 10 to 11 cents per square foot. So about 43 cents savings there on an annual cost basis. Additionally, the IAQP is allowed under various green certification programs such as LEED and WELL. They offer additional points when you use the IAQP. So I mentioned earlier the IAQP sits in or lives in standard 62.1, is referenced in the IMC, the NBCC, but it's also referenced in LEED and WELL rating systems. So I won't go into details there, but just wanted to kind of highlight that the IAQP is kind of an easy button to achieving a few additional points under LEED and WELL. Target applications for the IAQP, it's really all commercial spaces under 62.1, except for spaces with a lot of exhaust. So the high exhaust would be relative to how much ventilation air you would typically need to bring in for the VRP. So examples of high exhaust buildings could be hotel guest rooms or multifamily residences where you have 50 CFM per toilet fixture, and you have a lot of exhaust from the toilets relative to the VRP or the prescriptive outdoor air requirement. So in those building types, you can look at the IAQP in certain systems that perhaps serve amenity spaces or common areas. And then similarly with kitchens and labs, those are also exhaust driven, require massive amounts of outdoor air to pressurize those spaces. But maybe the office spaces adjacent to the lab, or maybe the seated dining area adjacent to the kitchen could be really good systems for using the IAQP. And then hospitals, of course, they fall under ASHRAE standard 170, so hospitals would not be a good application. So everything else, apart from that, is a really good application. Most notably, a lot of the work we've done in Ontario has been a lot of the IAQP projects we've done in Ontario has been in office buildings, K through 12, colleges, event spaces, transportation hubs, warehouses, and many other building types as well. So one of the reasons I'm really excited to have this opportunity this morning to talk more about the IAQP is because the IAQP has been fully revamped over the last, I would say, 3 years. And that's really to help enable many of you who perhaps are designers of buildings to take advantage of the IAQP to help achieve decarbonization and load reduction goals. So some of those major updates I'll be discussing in the next few slides. So here you can see that when we apply the IAQP, there's essentially 4 steps. The first step is to develop a criteria for indoor air quality. So that involves having a list of contaminants and their limits. Previously, that was not defined. Now, ASHRAE has defined that for us. So I like to think of this as designing, say, or sizing a cooling, or determining the total cooling capacity for an HVAC system. In order to do that, we need to know what is our set point for indoor temperature and indoor humidity during the summer season. So once we have a set point, we can reference outdoor air conditions and then size our cooling system. Similarly for IAQ, we need to know what are our set points for indoor air quality, or what are our concentration limits. That enables us to then right size our ventilation systems when using the IAQP. Step 2 is to understand for each of the contaminants we've identified in step 1, how quickly are they being generated? Previously, that was not defined, and now those emission rates are defined in the user's manual 62.1. And again, going back to this metaphor of sizing a cooling system, in order to size a cooling system, not only do we need to know our internal set points for the summer, we also need to know how quickly is heat generated from lighting, equipment, people in the space, how quickly is heat being lost from the building envelope. And then we can size a cooling system by doing that in mass balance. Similarly, with IAQ, we need to understand generation rates, and that's well documented now by ASHRAE. Third step is then to apply air cleaning. And to apply air cleaning, we need to know how efficient is my air cleaning system against the contaminants that we identified in step 1. Air cleaning efficiency testing requirements were previously kind of vague and not properly defined by ASHRAE. ASHRAE since has published really rigid and robust requirements for how air cleaning efficiency should be measured, so that you as a designer can feel confident with applying air cleaning into your ventilation system selection. So that air cleaning efficiency comes from a third-party test that's prescribed in Addendum N in 62.1 2022. And then the last step is to plug in, inputs from step 1, 2, and 3 into a IAQP calculator, and that calculator is also published by ASHRAE. And previously, the calculator did not exist for designers. It was a manual calculation. So in the next 4 slides, I'll go through each of these steps with just a bit more detail. So as I mentioned earlier, step 1 in the IAQP process is to develop a list of contaminants and their limits. So this is table 6-5 from standard 62.1. And this is an example of what those contaminants are that we need to design for in commercial buildings and what those design limits are. So this is a really nice table because it allows us to kind of level the playing field for how we solve for indoor air quality in a commercial space. Emission rates. So I mentioned, we have emission rates documented by ASHRAE. An example of that is shown on the table on the right. This comes from the ASHRAE 62.1 User's Manual. And what you see here is that the emission rate of these different contaminants is a function of the floor area of the space. So here you see meters squared, right? So if we know the size of the space, we can calculate the total load of these different contaminants. These emission rates will vary depending on the space type. This is an example for offices, but depending on the space type, you have variation in emission rates. These emission rates are packaged into Appendix N of 62.1, and they come from decades of research supported by ASHRAE, where different types of spaces are studied and emission rates were then populated. Step 3 is, making sure we have an understanding of how effective an air cleaning device may be against those different contaminants identified in step 1. So this is an example table on the right showing for different contaminants the efficiency of an air cleaning device against those contaminants. These air cleaning efficiencies are measured by a third party using the test method outlined in standard 145.2. So this is an example of what those air cleaning efficiencies look like. I encourage you to, as you explore different types of air cleaning technologies commercially available, to ask the manufacturer for their ASHRAE 145.2 air cleaning efficiency reports so that we're using the right inputs in the IAQP calculator. So speaking of the calculator is I'll get to that in a second, I promise, but the calculator itself has this equation built in. So let's spend a few minutes here going through the mass balance IAQP calculation. So this calculation, what we're doing is we're balancing the total load of a pollutant. So that's N. We're balancing the total load of a pollutant using with outdoor air, so that's labeled as dilution, and with air cleaning, so that we're always below the concentration limit of that said contaminant at the breathing zone. So CBZ is a concentration limit. So if you can follow my mouse here, I'll kind of hover over the different variables as I explain them in more detail. So if we talk about carbon dioxide, for example, maybe you're including carbon dioxide as one of your contaminants that you're designing for, and the limit for that is, let's say, 1100 ppm. That's CBZ. The total load of carbon dioxide, N, is a function of the number of people in the space that are emitting carbon dioxide times the emission rate per person. So if we know the number of people, we can calculate the total load of CO2. Now there's a negative sign in front of dilution and a negative sign in front of air cleaning. So if we know the outdoor concentration of CO2, we can figure out how effective outdoor air can be to offset some of my CO2 load in the space. And if we know the efficiency of removing CO2 from the air cleaning device and the amount of airflow going through the air cleaning device, we can take credit for some air cleaning to offset some of my CO2 load in the space while being below the concentration limit. So this is why the IAQP is a really clever design tool, is that it has two unknowns, outdoor air and air cleaning. You can find the right combination of these two unknowns to achieve project goals related to load reduction and energy efficiency. An example of optimizing around load reduction could be that maybe in your building, I have a total prescriptive exhaust requirement of X CFM from all the bathrooms in the space. I multiply that by 1.1 because I need to positively pressurize my space. So I know how much outdoor air I need to bring in to minimally pressurize my space. I can plug that into dilution, and then I can solve for how much air cleaning I need. So that way we're maximizing OA reduction down to what you need to maintain slightly positive building pressure. So this equation is applied not just for CO2, which I talked about in my kind of example, but it's applied for every single one of the contaminants that are established in step one. And a lot of times the driving contaminant is formaldehyde. Formaldehyde tends to have the highest generation rate per square foot, and thus ultimately dictates how much air cleaning and outdoor air you would need to bring into a ventilation zone. All right, so I mentioned earlier that in step 4, there's an ASHRAE calculator. So this calculator was published last summer as addendum C to 62.1. Within this calculator, you have really similar inputs to VRP, such as floor area, occupancy, system efficiency. And in return, you can simply, you can easily calculate your ventilation requirements and your air cleaning requirements for a system. As a follow-up to today's, session, we can consider having a separate session on how to use this calculator as well. So these are some of the updates I talked about over the last 4 slides. Addendum AA defining the concentration, defining contaminants and their limits. Addendum N setting regulations around how air cleaning efficiency is being measured. And then addendum C, that was a publication of the ASHRAE calculator itself, which is available for download on the ASHRAE bookstore. All right, so over the next few slides, I'll go through a sample calculation using a sample building, and we'll go through a VRP calculation, and then we'll go through an IAQP calculation. So to keep it simple, let's look at this giant 100,000 square foot office building as a single zone. In this 100,000 square foot office building, applying a default occupant density of 5 people per 1,000 square feet, we have 500 people. We're supplying cool air above the breathing zone, so the distribution effectiveness is 0.8. And in this building, we also have about 2,000 CFM of exhaust from all the prescriptive end uses, such as bathrooms, janitor closets, and from a few electrical closets. So let's start by looking at the VRP calculation for the sample building. So the VRP calculation involves people components of roughly 5 CFM per person, and then a building component 0.06 CFM per square foot. As we talk about the VRP, I want to be fair and also bring to light that a lot of times we pair VRP with DCV as a control strategy for modulating outdoor air during building operation. When we use DCV, we can modulate only the people component of the total outdoor air requirement. So the floor area component is a constant, and we can toggle kind of the people component in real time. A lot of times we use CO2 sensors as a proxy for occupancy to help implement a DCV control strategy. All right, let's take a look at. So yeah, that's the VRP calculation. We'll go through the results of this shortly. And as I mentioned earlier, we're also using that same sample building to run through an IAQP calculation. This is a close-up of the IAQP calculation. So when we plug in the total square footage, the type of building, and the occupancy of the building into the IAQP calculator, we're able to solve for the total load of a pollutant for each one of the pollutants. And we're able to get a result for how much outdoor air and air cleaning we need. So let's take a look at some of the results. So with VRP, our total system outdoor air requirement is about 10,625 CFM. As occupancy kind of toggles between design, so 500 people down to, let's say, 100 people, we can, vary outdoor air by roughly 20% during operation. So there are some savings through DCV, but it's kind of capped at that floor area component, which is about 70% of the total VRP requirement. So in a VRP case, I'm sizing a 10,625 CFM ventilation system. With the IAQP, I am now able to size enough air cleaning. In this example, it's about 4,000 CFM of cleaned recirculated air. And by doing that, we're able to reduce the total ventilation requirement to 3,260 CFM. So, there's almost a 70% savings here against the VRP. And the IAQP, because it's a load calculation, this is now driving the sizing of your ventilation system. So we can permanently achieve this reduction in outdoor air, whereas with DCV, it's kind of just a control strategy. We can't size our equipment for these reduced outdoor air levels. So the IAQP allows us to now permanently design for a smaller system, and that can have a systemic impact on how you size other building systems like chillers, boilers, energy recovery units, etc. So over the next few slides, I'll go through a few case studies. I think there's 2 or 3 case studies. The first case study is the Ottawa Central Library. This project was targeting LEED Gold certification. It was also targeting enhanced levels of indoor air quality going beyond, code minimum requirements. And it was also targeting peak load reduction for cooling to help drive some CapEx savings across the HVAC systems. And of course, it was targeting reduced energy consumption as well. So what we did was we looked at performing the IAQP calculations for individual systems serving individual zones in the building. The dark blue bars represent the baseline of the VRP outdoor air requirements, and the green bars represent the IAQP outdoor air requirements. So you can see here is that we were able to reduce ventilation requirements by about 30% in this example, going from 38,000 to about 28,000 CFM of outdoor air when using the IAQP with air cleaning systems. We also modeled the indoor air quality using the IAQP calculation tool. We were able to determine that with the reduced flow of outdoor air, because we're adding in high efficiency air cleaning systems, we're also able to achieve all of our design targets for indoor air quality. Some of those targets are highlighted in the orange bar here. So you can see here that, for example, the formaldehyde concentration at VRP outdoor airflow would be around 25 parts per billion. With the IAQP and with using a high efficiency filtration system, we're able to achieve about 16 parts per billion of formaldehyde. And you can see the impact across CO2, particulate matter, and ozone. For particulate matter and ozone, you see that the reduction is a lot greater. And that's because particulate matter and ozone are largely coming from the outdoor air. So by using the IAQP, we're reducing outdoor air and reducing the load of ozone and PM 2.5 in the indoor environment. I mentioned earlier that there are LEED points available. So with the Ottawa Central Library, we were able to use the IAQP to earn about 7 additional LEED points. So some of you may be aware of the fact that you could get 1 point by increasing ventilation by 30%. So instead of that, the design team here applied the IAQP and submitted for earning about 7 points available through a pilot credit under LEED, which you can see here, the breakdown comes from a few different credits: enhanced indoor air quality strategies, innovation, and construction indoor air quality management. Another project example is a building here. This is a university building, and this building was previously a shopping mall being converted to a college building. The building was originally designed for 250 occupants, And the new design was looking to support almost 1,800 occupants. So the idea here was to leverage existing infrastructure, existing ventilation systems to help reduce some first costs associated with installing larger and new HVAC or ventilation systems. So in this project, the design team was able to use air cleaning and use the IAQP to offset the need for new ventilation systems with air cleaning and enabling existing infrastructure to be left in place and be reutilized with some refurbishment. And it was essentially able to reduce the total load as well as the energy usage for the site. So for the same office building, for the same university space, you can see here kind of a system by system breakout of the baseline or the VRP ventilation rates versus the IAQP ventilation rates. So there's 4 air handling units here. Each one of them achieved about a 50% reduction in ventilation requirements using the IAQP with air cleaning, and that's represented in the lighter green bars on the right side. So the total cooling load reduced by about 86 tons, and there was about $15,000 of savings annually in energy costs. A lot of those savings are coming from reduced capacity charges for the electrical system because we're saving energy here, or we're reducing load here during peak summer times. And as a result of that, we're also saving about, or we're also earning in this project earned about $40,000 in utility incentives. I went through a few case studies I worked on myself. There's also many case studies publicly available that talk about the IAQP. In 2017, the U.S. Department of Energy evaluated different air cleaning technologies and identified the IAQP as a high potential solution for achieving good indoor air quality and good energy savings. And that's outlined in a 2017 report by the Department of Energy. In 2020, the United States GSA included air cleaning and the IAQP as a preferred pathway under the Green Proving Grounds program. So it's essentially encouraging designers of government buildings to use the IAQP with air cleaning on the design of new ventilation systems. And then a few years ago in 2022, Harvard University did a full M&V study that involved multiple buildings on campus, studying the impact of using the IAQP on both air quality and energy efficiency across multiple buildings on campus. I'll go into the Harvard study since we have a few minutes before we turn it over for questions. I'll go through the Harvard case study briefly here. So at Harvard University, there were multiple buildings that utilized the IAQP to save energy and reduce total load on the central district chilled water plant on Harvard, as well as the central steam plant. So in this case study, we're looking specifically at Robinson Hall, which is a combination of administrative offices as well as some classrooms, about a 45,000 square foot building. The baseline outdoor air requirement was 6,500 CFM, and the IAQP outdoor air requirement was almost 65% less, which is 2,100 CFM of outdoor air. So the outdoor air was supplied by 2 air handling units. What you see here is essentially one of the air handling units, so that's AC1. AC1 is equipped with an air cleaning system that's shown here. So what that air cleaning system is doing is it's taking return air or indoor air from the primary return air duct from the spaces. It's taken about 5% or 1,000 CFM of that return air, and that return air is being collected by an air cleaning device. And that clean air from the air cleaning device is being resupplied back to the air handling unit in the return air system downstream of where we're picking up the dirty return air. So by cleaning only about 5% of the return air, because we're cleaning at a really high efficiency and we're applying the IAQP, we can achieve almost a 65% reduction in the outdoor air requirement. In this example, you also see this red line. This is for regeneration. Regeneration can be achieved depending on the air cleaning system you're looking at. Some air cleaning systems have the ability to essentially replenish their filters through a regeneration cycle. And to do so, you need to exhaust that regeneration air out of the building. And that's what's shown here in the red duct. And that's just integrated into an exterior exhaust louver on the side of the building. So at Robinson Hall, we were able to work with a balancing contractor to rebalance the outdoor air requirements of the two air handling units. So the baseline of the VRP outdoor air requirement was 3,000 to 3,500 CFM for each of the air handling units. And then we were able to reset the outdoor air damper to a lower minimum using, obviously a balancing practice. And we were able to rebalance that so that the new or the IAQP outdoor airflow rate was set to about 1,000 CFM of outdoor air. And on the right side here, you can see that because this was an existing building, we were able to do some nice testing of indoor air quality before and after. So the before case is represented on the two columns on the right. You can see here that without air cleaning and with higher levels of ventilation, if we look at formaldehyde specifically, the formaldehyde levels were about 23 to 31 micrograms per meter cubed. This was measured across a few different locations in the building. And after the airside systems are reset to the IAQP outdoor air levels and the air cleaning systems were commissioned, the measured formaldehyde levels actually went down to less than 20 micrograms per meter cubed. And all other contaminants that are defined by ASHRAE as design contaminants were also well below the baseline, were comparable to the baseline levels, but well below the ASHRAE defined limits for acceptable indoor air quality. So this is a really nice study. It demonstrated that we can safely use the IAQP to achieve acceptable indoor air quality with much less outdoor air and much less energy. Speaking of energy, you can see some of that here. On the left side, you see that the baseline energy usage, a big chunk of that is from heating the ventilation air, is represented in this bar here. And as part of the measurement and verification study, utility grade meters and sub-meters were used to validate the energy savings. So you can see here that, based upon the findings, the university would consider using the IAQP in existing buildings as well as new construction. And that's largely because of, the fact that this M&V effort was able to demonstrate the reduction in contaminant levels as well as the reduction in energy. So that brings us to, I'll skip through some of this. That brings us almost to time. I talked about these highlights, reducing load, which in return reduces CapEx for HVAC systems, reducing energy consumption, improving indoor air quality in many cases, earning LEED and well points as well. And what I started with kind of towards the beginning of the session was these different market drivers around decarbonization, net zero, resiliency, as well as financial uncertainty. So as a designer, as a building owner, I think the IAQP can be a really clever design practice to achieve or address these market drivers. And with that, I wanted to, again, thank you for your time this morning and turn it back over to Matt to help look at any questions that may have come up during the session. And we have about 10 minutes now to do a Q&A.
Yeah, thanks, Anurag. That was great. If anyone does have any questions, they can throw it in the chat function or the Q&A function at the top here on Teams. I think we only really had one, and it was about the recording, which has been answered. So none in there currently. So if there are no questions that you wanted to ask, we can kind of end the session. If there is anything, please throw it in the chat. We'll leave it open for the next couple of minutes here. But if that's it, that's really all we have. All right, well, a couple of thanks in there, but I don't see any questions. So if you guys do have any questions about IAQP or enVerid, feel free to reach out to your local Odell representative and they can help you out with that. And again, thanks, Anurag, for stopping in and giving us a bunch of new knowledge.
You're welcome. Have a good day.
Thank you. Bye, everyone.